So welcome everyone back to the CADRE series of webinars from our fellow teams. Just to remind you, if you're not familiar with CADRE, it's a data sharing platform in the cloud that we're building here. And we're also supporting the group of researcher teams who is presenting in this series webinar. By working with them, we provide data support, in particular Web of Science and Microsoft Academic Graph datasets. And you can reach us at our website, email, and Twitter. Just want to acknowledge our support from IMLS and Web of Science, as well as Microsoft Research. So here's our partner institutions who's supporting us. Besides this list here, we just want to announce that most recently, University of Maryland just joined us. So we have a new member library. So the CADRE community is growing. A brief recap of what happened earlier this year. The webinar started back in February with our alpha launch. There's 2 fellow presentations already prior to this one in March and April. We took a little break in May, because we're meeting with our council, owners councils. But now today is a continuation, and we will be continuing the series for the rest of the year. So this is, I think this is back in March. Our one team from OSU presented. Last presentation was from our MSU team. So you can check out their presentation in our website. They all have been recorded, so you can watch them if you have missed them. Coming up next month, we already scheduled a back-to-back doubleheader at the end of July from our University of Minnesota team. So please check us out at July 22nd and July 29th. This is a big team, so they have 2 separate presentations. So here's the link where you can find all the information and resources. And without further ado, I just want to introduce today's presenting team from back then, still in Indiana University and Nanjing University. Their project title was Understanding Citation Impact of Scientific Publications through Ego-Centered Citations. But today, a lot of things has changed. First of all, congratulations to Yibu, who is now starting his new career at Peking University. Unfortunately, he is still under quarantine right now. He just got back to China and still in the last day of his quarantine, but he's with us today. He will be able to answer questions, I think. But due to internet connection stability problems, Chaoming will be the presenter today. And Chaoming's title today is Describing and Predicting Scientific Breakthroughs Based on Knowledge Structure Variation. As you can see, that's a particular aspect of how you can understanding citation impact from citation networks. And last but not least, Yingding, also is part of this team, has recently moved her job to UT Austin. Unfortunately, she cannot be here today. So without further ado, I'll stop sharing my screen here and let Chaoming speak.
Okay, thank you. Thank you, Xiaoran. We really appreciate it, and we are really honored to be the CADRE Fellows presenters today. So I hope you can see in this presentation how we make good use of the CADRE data and see our results in several of our works. So as Yibu is in quarantine, and he has a very poor internet connection. So I will present our works, and I look forward for any comments and critics at the end of the presentation. So now I will, the topic of my presentation is identifying and predicting scientific breakthroughs based on knowledge structure variations. It is an application of our CADRE project about citation impact and the Eagle citation network. Okay, I will start with the first part, identifying citation patterns of scientific breakthroughs. As we know, scientific breakthroughs are essential for the advancement of science system. But the identification and the recognition of scientific breakthroughs is not an easy task. There are two possible reasons. The first reason is that scientists themselves may resist to accepting new scientific discoveries because scientists, like all human beings, have psychological biases that manifest strikingly in the face of change. And the second reason is that the selection of research topics influences the attention received from scientists. For example, the scientific ideas emerging from crowd research areas face fierce competition for attention. Despite these difficulties, there have been some efforts in identifying scientific breakthroughs. We summarize the efforts into two research streams. In the first stream, researchers study, they take advantage of temporal citation profile of breakthrough works. Eminent researchers who are likely to create breakthroughs and scientific works with significant but delayed recognition, which is also called sleeping beauties in science. And in the second research stream, researchers study the citation network and the innovativeness of a paper and a paper's intellectual positioning in the knowledge network to quantify and to identify scientific breakthroughs. But most of the efforts only focus on the external characteristics of publications. Thus, they are loosely coupled with the intellectual structure of scientific breakthroughs. So they have limited power of discrimination on breakthrough ideas and non-breakthrough ideas. Since citation count alone has limited predictive power, can we dive into micro aspect of the citation process? So in this project, or in this study, we propose a question: what are the features in citation patterns that distinguish breakthrough ideas from their non-breakthrough counterparts, if any? We select Nobel Prize winning papers as scientific breakthroughs recommended by Shen and Brabasi. We get 116 papers from 4 disciplines of physics, chemistry, physiology, and medicine and economic sciences. And then we construct a control group of non-Nobel Prize papers. In this group, each of the paper has the same publication year, same venue, and roughly equal citation impact with one corresponding paper from the Nobel Prize group. We then collect citation data of these two groups of papers. Actually, we collect citation data within 4 citation generations from the in-house version of Web of Science database supported by CADRE platform. And we finally obtained 19 million citation pairs. And then we calculated a series of metrics to compare the citation patterns of 2 groups from 2 dimensions. The first dimension is temporal dimension, and the second one is structural dimension. Next, I will introduce how we calculate those metrics. So in the temporal citation dimension, we adopt a perspective of citation life cycle. You can see in this figure, the x-axis is time and the y-axis is yearly citations a paper receives. So after a paper's publication, it will undergo landmark moments, such as when it receives its first citation, its citation number takes off, and its first citation peak appears, and its citation summit appears, and then the citation numbers declines. So we collect the yearly citations from the publication year onward and calculate 4 metrics. The first metrics is 4 groups of metrics. The first group of metrics is about first citation. It is a time span between publication of a paper and its first citation, along with citation counts in the first cited year. We take note of the year T when the publication was first cited, and the citation counts CT at T, where T satisfies this formula. And the second metric is called citation takeoff. It is the turning point at which a work starts to get attention. We adopt Kerr's approach on identifying takeoff point and calculated the cumulative citations when the paper take off. The second metric is first citation peak, which is a point at which yearly citations form the first peak on the citation curve. So how to operationalize the citation peak? We consider it a peak if that year's citation count is greater than in each of the previous 3 years and no less than in the 3 subsequent years. And then the fourth metric, temporal metric, is citation summit. It is a point where work gets the highest yearly citations. This is relatively simple to calculate. And then for the structural citation dimension, we can see in this figure, a paper also has a structural dimension in its citation structure. So when a paper is published, it will be cited by several papers, and then these papers will be cited by following works, forming such a tree, citation tree. So the citation structure is represented in this work, represented by 4 generations of citations. That's why you can see why we get so large citation data. We collected citation data within 4 generations to the work under study. And the citations are made within 4 years of initial publication. the structural metrics are calculated for the first 1, 2, 3, and 4 generations of the citing articles citation network within 4 years of publication. And they include average clustering coefficient, network density, connectivity. All are common metrics about networks. So what is the performance of Nobel Prize papers? Our results show that while most of the Nobel Prize papers received attention shortly after publication, a small proportion remained uncited until 3 to 9 years later. And a significant number of Nobel Prize papers took off 5 years after publication, with takeoff time varying from 2 to 25 years to even 25 to 45 years. In such a long preparation period before takeoff, several papers accumulated more than 100 citations, but most papers obtained fewer citations than that. And we also observe a long time span between publication and the citation summit. This suggests a long period of citation growth of Nobel Prize papers. Statistics show that average papers reach their citation summit 2 to 6 years after publication, but Nobel Prize papers tend to lag behind. And for most of them, the summit comes after the 6-year mark, with some peaks appearing even more than 30 years after publication. Next, we compare the Nobel Prize group with control group in both in temporal dimension and the structural dimension respectively. As you can see in table 1 and table 2, most metrics cannot distinguish the two groups. But we do find several metrics that can separate the two groups. In temporal dimension, TOS, which means takeoff span, and TC, which means takeoff citations, they have significantly descriptive power. And in the structural dimension, we can see average clustering coefficient and connectivity. They can separate the two groups. And actually, the discriminative power is most significant in the first 1 and the first 2 citation generations. Specifically, Nobel Prize papers took off 4 years than non-Nobel Prize papers, and they had far more accumulated citations, nearly 2.4 times at takeoff. This verified the fact that scientific novelty has far-reaching impact, though its recognition lags behind. The finding that Nobel Prize papers have higher average clustering coefficient and greater connectivity implies that there are more interlocked structures in these papers citing networks. And this suggests that scientific works with significant breakthroughs can inspire subsequent works that are also relevant to each other. So the takeaway messages for this part are as follows. So first, we can say that most citation measures cannot distinguish Nobel papers from non-Nobel papers. However, 3 measures do significantly distinguish the two groups. They are citation takeoff in temporal dimension, and average clustering coefficient and connectivity in structural dimension. This implies that although scientific breakthroughs are not easy to quantify, they do leave visible marks in the process of citation diffusion. And these marks provide potential traces for identifying innovative scientific works at an early stage. And our results show that scientific breakthroughs reveal unusual characteristics in the first 1 or 2 generations of citing structures shortly after publication. In this case, 4 years, within 4 years after publication. We can see the 3 metrics. Citation takeoff is from the temporal dimension. So it takes time to calculate this metric. So the remaining 2 metrics, average clustering coefficient and connectivity, they have more potential in identifying early scientific breakthroughs. So in the next part, I will present how we utilize the structural dimension to predict scientific breakthroughs. The data we used are also the 2 groups of, based on the 2 groups of papers and their citation data extracted from Web of Science. But we focus on the direct citing network. Since we find in the first part that only the first 1 or 2 generations have most significant power in distinguishing the 2 groups. And we also focus on the citing networks within 4 years of the target paper's publication, as early citing structure is more useful in prediction. So if we use citation data 10 years, for example, 10 years later, that will not be prediction. I think that's maybe a very verification. So we use citing networks within 4 years of the target paper's publication. And in this part, we calculate more structural metrics. For example, if there is a citation network G with a set of nodes V, and they are actually papers, and the set of edges E, and the edges are citation relations, we calculated the following metrics. The first one is number of nodes, which is the number of citations to a paper, abbreviated for NON. And the second metric is number of edges, which is number of citation relations in the citing networks. And the average discrete network density, average clustering coefficient, maximum betweenness centrality, maximum closeness centrality, maximum eigenvector centrality, number of components. Because we don't know which metrics have the discriminative power, so we calculate as much metrics as possible to test their effects. Before prediction, we find that there exist differences in the knowledge accumulation process for the 4 fields of Nobel Prize. You can see in this table, the values in the table are the mean value in each discipline. We'll take publication year, for example. We can see the economic papers are the oldest, and the medicine papers are the newest, and the chemistry and the physics papers are in between. But when we look at the number of notes or the number of citations to those papers, we find surprisingly that the oldest paper from economic sciences, they receive the least citations, but the newest paper from medicine discipline, they receive the most citations. So this is an example of the difference between the disciplines. And from other metrics, we can actually find that these disciplines can be categorized into two groups. The first disciplines are from natural sciences. They are more likely each other. And the second, the economic sciences is from a relatively different field. So a brief observation. Yeah.
Can I ask a question?
Yeah.
Last slide, please.
Yeah.
So a little bit confused about the number of components metrics here. So so you're building a whole network of all the papers and measuring their connections there?
So the number of components is it is a metric of the citing network of focus paper, and we eliminate the focus paper in the network, in the citing network. So there can be many components.
And this is the strongly connected components in a directed network, right? Or
yes, yes.
Weakly, sorry. Yeah, I see.
Okay. So a brief observation is that physiology or medicine accumulates citations the fastest. Economic sciences do the slowest, with chemistry and physics in between. And for in terms of the number of citation relations, a similar finding, we also have a similar finding. Physiology or medicine greater than chemistry, greater than physics, and greater than economics. But in terms of network density, which measures the overall connectivity of a network, the order above is reversed. Economic sciences is the highest, and physics is the next, chemistry is the third, and physiology or medicine is the lowest. In addition, we find two metrics can distinctly separate natural sciences and economic sciences. They are average clustering coefficient and average degree. For average clustering coefficient, chemistry, physiology, or medicine and the physics are very close, but economic sciences have much lower values. And for academic average degree, economic sciences are also show also the lowest value, while other three natural sciences are much higher. For maximum betweenness centrality, maximum closeness centrality, and maximum eigenvector centrality, they can also consistently show the difference between the two groups of disciplines. And in terms of the number of components, physiology or medicine has the largest number of components in the citing networks. We also have a finding that economic sciences papers were the latest to receive Nobel Prize after initial publication. They received the prize roughly 30 years after publication, while papers from chemistry, medicine, and physics got the award relatively a little bit faster. So next, we compare the two groups year by year to find which metrics can distinguish the two groups in each year. As we can see, in the first year, second, fourth, third, and fourth year, there are 4 metrics in bold, which are number of edges, average clustering coefficient, maximum closeness centrality, and the average density, they have a significant effect. But all other metrics cannot separate the two groups statistically. And in addition, the difference in number of nodes, so this one, it is only significant in the first year. But the difference fades away statistically speaking through the following 3 years. In fact, the two groups have been relatively close in average citation counts in the first 4 years, with Nobel group a little bit higher. This reveals that direct citation counts cannot effectively distinguish Nobel group from control group in the early stage of breakthrough formation. So to further quantify scientific breakthroughs based on knowledge structure characteristics, we run a series of regression models. In these models, the dependent variable is whether the paper is from the Nobel group or control group. And the independent variables are the structural metrics mentioned above from paper's citing network. The regressions lead to the finding of a series of metrics that can effectively characterize the breakthrough potential of a paper. This is the regression results for economic sciences, and then natural sciences separately, with all 4 years data together. For economic sciences, we can see that there none of the metrics are significantly have significant effect on the output variable. But for natural sciences, 3 metrics have significant effect on the output variable. They are average clustering coefficient, maximum eigenvector centrality, and average density. So this table suggests that we need to proceed with our analysis taking the disciplinary difference into account. And further, to get better model performance, we might also need to investigate the networks year by year, rather than all 4 years together after the network's formation. So this is the results of economic sciences year by year. We can see the overall performance of the models is best in the second year, because the probability greater than chi-square is the lowest in the second year, and the pseudo R-square is the highest in the second year. We also find maximum eigenvector centrality is significant in the second year, and network density is significant in the third year. So this is the results for economic sciences. And for the results of natural sciences, the overall performance of the model is still the best still in the second year, because you can see the probability is the lowest here, and the pseudo R-square is the highest here. But we can see there, so we can say that the second year is the best timing of observing breakthroughs, or predicting breakthroughs. And we can also see in this table that for natural sciences, there are much more metrics that can that are significantly that have significant effect, and in this way we can conclude that maybe we can conclude that natural sciences are more easy to predict the breakthroughs than economic sciences. So with all the observations in mind, we next predict whether a scientific paper will be a breakthrough in the future based on its early citing network structure. The prediction is conducted at year 2 and year 3, as we have shown in the results above that the second and third year they are better predicting timing than other years, and we also separate economic sciences and natural sciences, and we also conduct a 5-fold cross validation procedure to test the performance of our prediction. So breakthrough prediction in natural sciences, we tried various combinations of predictors. You can see in this table for natural sciences, in model 1, we use only the number of nodes, which are also the number of citations, to predict breakthrough. Actually, the results is 0.451, and this is result even poorer than a random guess. So this suggests that citation counts is not a good indicator for breakthroughs. Maybe it's a worse or bad indicator. And in the following models, we tried different metrics. In model 7, we tried the 4 metrics that are significant in table 7 at year 2. We used the 4 metrics as predictors, and it turns out that the AUC increases to 0.675, so 0.675. It is the highest value in all the models. And for the economic sciences, we use the we use 2 models, model 1 at year 2 and model 2 at year 3. Model 1 presents a better predictive power than model 2 does, but the standard deviation of model 1 is very high, so the performance of model 1 is relatively unstable. So this is the result of economic sciences, and these results also verified observation of a previous observation that breakthroughs in economic sciences are more difficult to predict than breakthroughs in natural sciences, and the prediction is more unstable. So I think the takeaway messages for this part is that scientific breakthroughs do impose particular influences on the knowledge structure of science. And this observation is useful for predicting scientific breakthroughs. And second, there might be optimal network layers and timings for observing the traces in knowledge structure left by scientific breakthroughs. So if we want to predict, make the prediction more practical, more useful, we might need to think about the optimal network layers and optimal timings. And third, differences among disciplines should better be taken into account when identifying and predicting scientific breakthroughs. So in our prediction, the best result is best result of AUC is 0.675. It is not a very satisfactory result for prediction tasks in computer sciences. But we think the task of predicting breakthroughs is relatively hard, and there are many factors that influence the formation of breakthrough. We haven't figured out these factors. So we will, I think in the next stage of our CADRE project, we plan to collect more breakthrough cases and collect more data to verify the results and improve the accuracy and performance of our prediction. Okay, that's my presentation, and thank you for inviting us and for your kind attention. I and Yi look forward for any questions and comments.
Great presentation.
Thank you.
We have plenty of time, so if the audience has any questions, feel free to ask. Yeah, unfortunately, we don't have as many audience today. I guess I'll start with the first question.
Okay.
So I think it's a great observation that different discipline has very different patterns in their citations, and especially economic sciences. If you're, I'm not that familiar with it, but I've heard they have very slow publication cycle. They have very, basically their style of publishing paper is very different from natural sciences. So I think a lot of less citations and more dense connections is kind of not surprising. But my question is, since you're only observing these Nobel winning papers, I would expect some of them, even within the same discipline, have very different patterns. I've heard they're Sleeping Beauty, one that didn't get cited until they get an award or something like that. And do you think the sort of individual differences really impact your performance? Because you mentioned that your AUC and in the end is not, very good. I would expect. How do you expect maybe these outliers is really affecting your model performance there?
Yes, very good question. I think there can be individual differences even in the same discipline. So we plan to enlarge the sample of our data. Now we only use Nobel Prize winning papers. For example, we can collect papers from other prizes such as Fields Prize and and breakthrough prize and Turing Prize, so on. So that's our plan in the next stage. So if for your question, if we see this, sorry, not this. If we see this table for natural sciences, they are relatively easy to predict because you can see the AUC is 0.675 and the standard deviation is only 0.07. So natural sciences, I think, relatively easy. But what I said in economic sciences, the results is not very stable because the standard deviation is 0.21. And I think in economic sciences, they are not only about economics. They have scholars doing sociology research, maybe, and doing management research, and maybe human resource and accounting and so on. So I think economic science is relatively a broad term. So how to solve this problem? So in the future, we plan to enlarge the sample of our data.
I see. I think that makes sense. To follow you up, since you showed the small variance in the natural sciences, does that mean there's only so much you can tell from citation structure? Maybe you need additional information to further improve, to discriminate between breakthrough and non-breakthrough, maybe even text topic analysis of that kind?
Yes. So we in this project up until now, we only use the network structure, and I think as you said, we can take advantage of the text data and maybe the semantic of the papers. So this maybe can improve our performance.
Yeah, if we can in the future, if we can use the text-related metadata, if we can supplement that kind of metadata into the citation data, I think we can incorporate more information such as the different weights of the citation network. Then we can have a directed weighted network, and I think that is more informative to us. And I believe that it will increase the performance of the prediction, I think. Yeah.
Thank you. We still have time for more questions.
Shaoran, Jane here. I have a clarification question to Xiaomin. Can you project again the factors that you considered in your model? Because I'm just curious about whether you guys considered the type of authorship for economic sciences versus other sciences, because we know that in the social sciences field, and lots of bibliometric studies have been done related to this, that most of the time in those fields, it's either a single author paper or very, very few. So the collaboration is not really huge for the social sciences field, and versus the natural sciences where we would see even more than 1,000 authors. So that will definitely affect the citation dynamics. Was that included as one of the factors considered, or I probably have missed that discussion?
Thank you. That's really a great question. We haven't included this factor in our study, but I think it's very valuable since in different disciplines, scientists do science in different ways, and they have different collaboration patterns, and this can influence the citation, the way their work gets cited. So I think it's a really good suggestion, and we will add this factor in our future work to reduce, maybe to or control or reduce the collaboration pattern in different disciplines. Thank you for your question.
Okay, great.
Yeah.
So inspired by Jane's answer, Jane's question. So actually I have two thoughts. The first one is probably in the future we can first incorporate the team size factor, which is easier for us because we just need to count the number of authors in the paper. And secondly, if we can partly solve the author name disambiguation issue, probably we can go to the second stage, which is to, examine the details in the team, such as who collaborate with whom, like a high impact authors collaborate another high impact author or other cases. But I think the first step, which is much easier, is to simply count the number of co-authors in the paper, probably. Yeah. And thank you, Jane, for the question. Yeah.
Sure.
Yeah.
Can I have a follow-up?
Go ahead.
Yeah. So what was which database? Was it Web of Science that you guys used?
Yes, Web of Science.
Yeah. And I think that is great. But I'm not sure whether you've attended our webinar last time. And
yeah,
Web of Science limitations in terms of disambiguating or parsing the authors can be very challenging. But I want to point out, in terms of that data source for economic sciences field, we know that social scientists and economists and most of the publications are not really indexed in Web of Science. So for the economics field, they use more the REPEC database. So, and that's also one of, I share that because that's one of the challenges for us here when we do the departmental level analysis for research publications of folks working in the economics field, because they don't really publish, or their publications are not really indexed in Web of Science. So definitely there will be less outputs reflected in Web of Science database. So it would be great, as you said, that you're going to increase your sample size so that at least there will be a general like interpretation based on your sample data set and whether it's really a representative. But I'm sure that you guys will really indicate that that Web of Science is not really the source for economic sciences papers, because they publish more on either REPEC, the Social Science Research Network, and not really in the Web of Science database.
yes.
Thank you, Jane, for the comment. Yeah. I actually have no idea that's the case prior to your comment. And do you think perhaps Microsoft might have that coverage better than Web of Science?
I'm not sure yet, because we didn't focus on the fields for our study, but I'm hoping that they would cover more. Yeah, maybe that could be an interesting research to explore using MAG.
Yes. So in Web of Science, they have 3 core collections. The first one is last one, Social Science Index, and the second collection is the first one is Science Index, SCI, Science Citation Index, and the second one is Social Science Citation Index, and the second one is Art and Humanity Citation Index. So
yeah,
I'm
but
not
when
sure.
you,
Is it sufficient?
yeah,
Maybe
yeah,
it's more. Yeah.
yeah, but when you talk to the real people in the field, they would rather use REPIC as their data source for their
Sure.
publications. Yeah, not
I see.
really. So
Can,
I guess that's an important limitation that you guys have to mention in your research.
Yes.
can I share the link to the Radix? Is it open, or we? You have
Yeah,
to
it's
purchase?
open, but
Yeah.
it's so difficult. And they actually offer API, but it's a voluntary network of economic scientists, and I can definitely share the link. And let me Google it up, and I will share it in the chat box.
That's very helpful, because I haven't mentioned it today, but we are launching our new coronavirus related research, and it's kind of similar there because it's too recent. People are, it's a community-based effort putting together documents on archives to create a new bibliographic data set. And if we have to do this, maybe this is a separate project that this team can try to, utilize.
Yes, this is very, very helpful because economic scientists, they use REPIC most frequently than Web of Science or Scopus. Yes, so it's very helpful. Thank you, Jane.
All right, we're out of time, and thank you, Chao Ming, for great presentation, and Yibu and the audience. We hope to see you back in late July for our next back-to-back two-header from our Minnesota team. Thank you.
Thank you, guys. This was a wonderful presentation.
Thank you.
Thank you.